Alright, in today's video, I will try to explain my answer about the final exam. Then now we go to the question. As usual, the first thing that we can do is from the question is by drawing the free diagram. Is the free diagram will look like? Well, from the question we know that the Fy is 1000 Newton and the Fz is 2500 Newton. Fy is going to down, which is minus 1000 Newton, and Fz also to direct to the negative z, then Fz will become minus 2500 Newton. From this load, we can find the moment in the x direction, which is mx, and then mz. Then we can also determine the normal force due to the Fy, then the torque due to the load. And also in this tank filled with pressurized fluid that have pressure 9 MPa. Now we go to the dimension that given in the out diameter it is 42, the inner diameter it is 40, then the thickness is 1, and the outer radius is diameter outer over 2 will become 21 millimeter. The inner radius is diameter of inner divided by 2 is 20 millimeter. Then I will determine the area of the tank, which is P r squared, when r sometimes you can use P c, where c is equal to r. Or I just use the same r. I didn't change it to c. Same. Then P times 21 square minus 20 square, then it become 128.81 millimeter square. Now G, which is over 2L to the power of 4, when P over 2L O to the power of 4 minus L1 to the power of 4, then it become like this. The G become 54.16 times 10 to the power of 3 millimeter to the power of 4. And then in this kind of problem, the relation with the polar moment of inertia and the second moment of inertia, when I is equal to G over 2. Then we go to the next, which is the E is equal to Fy equal to minus 1000 Newton, Fz or equal Pz also, Pz equal to Fz, and Fx equal to 0 because there is no force acting at x direction. Then the Mz, the moment of C is in this direction, is minus 45 times 10 to the power of minus 3 times 1000, and become this. It's minus because this one is minus. So then mx is 75 times 10 to the power of minus 3 times 2500, and this become 187 and 5 Newton meter. Then the torque is the direct the I mean the distance times the load, then this become this 225 Newton meter. And I forget to mention about the this the I is half of G over 2. I is equal to G over 2. Then this is the I become. Now we go to the next. And for point B, part B, I mean, we need to determine the normal stress and the shearing stress at point A and also point B. Know that the location at point is point A, this is point B, this Y, Z, and X direction. This is thin wall filled with 9 MPa fluid. Then from the book chapter 7.6 to determine the normal stress pressure rate is from this equation. The sigma x is from the hoop stress and the sigma y is from the longitudinal stress. The equation was likely similar, but the difference is if the hoop divided by t, but the sigma y, the longitudinal is divided by 2t because from the sigma x we only use one thickness, and from the sigma y longitudinal we use all the part from the thin wall. So we use the thickness 2t. We input the number that we already know. The when P is the pressurized fluid and MPa, the R is the inner radius of the tank, and the T is the thickness of this. Then go to the normal stress due to bending. Then the sigma equal to MC over I. Then point and the axis is the mx. It's the derivative of mx over mxco over I equal to this 187.50.0, which is number to the equation. And we cut this for the then for the normal stress due to the normal force, this the E is equal to Fy. Fy is going downward, so minus 1000. Then we cut this number for the normal stress to normal force. And for the shear stress to the torsion, now equal to Tc over J. Then the T is the torque, and C is the out radius, and J is the permanent inertia. We already got off this number from the previous set. We just put and it's 87.2 mega. And for point B, the normal stress with internal pressure is actually the same. The point A, it's the same point. The sigma x equal to 108 MPa, sigma y 90 MPa. But for the normal stress to bending will be different since the sigma mc over I is equal to mz co over I. Mz is the moment that acting on y, I mean on point B. Then we cut this into the number to each equation and cut this value for sigma. Then at point then for the normal stress due to normal force is the same, and sigma P over A equal to this, and it's just same value with point A. Now I will continue the talk with the shear stress. Indeed, this shear stress at point B is affected by the shear stress to torsion and the shear stress to transverse shear. For the torsion, shear to torsion is really the same. The point A, it is the same value, the 87.2 MPa. For the shear stress to transverse shear, we have been it use the different formula. Formula is Q over IT when Q is this. Actually, Q is a y bar. Q equal to 8 times y bar. This is a simplified equation. This is equal from because this initial polar shape. Then we just need to input all of this equation value to this equation. Then we get the equation. Now, for the point P is the summation between this situation and the situation 126 Pascal. Principal slash everything at point A and so point B. This is the point A. The first thing that you can do is list all of the known components. This is sigma bending, sigma P, sigma Y pressure, and sigma X. Then sigma bending. This is like on A, point A less on the zero. So this is still in positive. This is population negative. This is 90, still sigma Y pressure, and sigma X 180. To determine the principal stress, we determine the sigma X and sigma Y, where the sigma X is this 180 and sigma Y is the summation between the sigma bending, sigma P, and sigma Y press. And I got this value 227 and 680 megapascal. Then to determine the sigma max, sigma min, the first thing you can do is the determining the sigma average and R. This is the sigma average. Input the value for sigma x, sigma y. I got this value. And also for the R, the tau is for A is 87.2. This is got from the previous slide. We got this for the R. Then the sigma average, sigma max is equal to sigma average. I mean, then the sigma max is this value 294 and sigma min sigma average minus r got this. But for the because this is the 3D plane and 3D should be 3D morphical, if the sigma min sigma min is not negative, then the sigma min will be 0. Then this is the value sigma min, sigma max, sigma min 0 and sigma max this. Then to determine the sigma max, this is the if this equation, this sigma max minus sigma min divided by 2, and look at this. Then this 144.105 will be used to determine whether the yield will occur or not. And this is the total P. This way. Now we go to the part C, point B. It is same list all the known properties. But for this point B, the problem will be negative because point B lies on the compression part. The other still the same. Then the sigma x still the same, the 180 MPa. Then sigma y is the same, the summation between sigma p, sigma p, and sigma y pressure. This I got this value. And we need to determine the sigma average. This is the point A, the different value that we the average that I got, and R. This is the same equation, but the tau is 126. Is different with point A and R. And for the sigma max equal to sigma average, this part plus this part, and we got this. Then the sigma means equal to sigma average minus R 113.7 minus 142.39. I got this. In Italy minus this. Then the sigma mean is 1. Sigma mean is minus 28.722 MPa, and sigma max is this. Then to determine the sigma max is same, the sigma max and sigma mean divided by 2, and I got this. Or if the sigma mean is negative, then the tau max is equal to R. Yes, it is same with this R. And for the principal planes, this is this same equation, different value. We got this, divide this, and we got this. Tan inverse, this 1.9, and tan to theta p is point theta p 31.16 and 121.12 degree. Then for this part D, and determine whether the yield will occur or not if the material that will be used is ISM836. From the data that I got, the sigma y for this is this point 150 megapascal. We know that 4.8, the tau max is equal to this 147. Using the maximum drilling stress criteria, the tau max equal to sigma y over 2. If the tau max is greater than sigma y over 2, then the yield will occur. But if the tau max is less than sigma y over 2, the yield will not occur. See, so in part A, we asked what is my suggestion if the B fail. Then from the calculation that I got, I think AB will fail at point A and should the atomic exit the sealing stress criteria. The improvement that I will do is decrease the infrared build so the thickness will be increased. For example, the thickness increased by 1, then the new is equal to millimeter. The mass to pressure field will change because the inner radius and the thickness will be changed. Then this value for sigma x, the new sigma y, this is the new average, the new R, and this new sigma min x and sigma max. Then the value of sigma tau max is 114.39 megapascal. Then for this value, this will not exceed the y over 2. So the yield does not or will not occur because it is less than the 125. Okay, that's all for me. Thank you.